Okay, so I'm gonna connect remotely to the CACs. I have this alias that I did to connect quickly. It's easy to make. First thing we do is TCSH, right? That's what we learned. Second thing we do is that we create if we don't have a directory for our project, we create it. So I'm gonna create it here. Let's say EECSC 585 fall 2012. Let's go there. And now we have to do a magic setup. Actually, I could have done that earlier, but it doesn't matter. Okay, now to start magic, I just type mag09. This means it's the channel length. What's the channel length? If lambda is 90 nanometer, it's 180, right? Okay. All right. So this is magic. Magic is basically two windows. One window where you actually make your layout and draw everything, and the second window where you do your commands. Okay, you need these two windows. You can't do everything in the graphical window. You're gonna need to go to the command line every now and then. Okay. Now, the first thing you should do is that you should enable the toolbar, which shows you all the layers that you have. For instance, this is polysilicon here. The second thing that you should do is that you should enable the grid. To enable the grid, you just press on G. And now let me zoom out. I zoom out using Shift and Z. And if it's Z alone, then it's zooms in. You have to know these shortcuts because otherwise it's very hard to zoom in and out. Okay, so it's Z and Shift Z. Now, this grid is very important. Any square in the grid is, do you have any guess what's the size of the square? Right. So any square is 90 by 90 nanometer, right? And this is a.
How did you open this?
Okay. Mag09. Yeah. You just do TCSH, then magic setup, and then mag09, right? Okay. So this is the smallest unit I can do. I can't do any smaller than this square. Now you can see I have this this rectangle, right? And at first it's gonna be very tricky for you to handle this rectangle, because if you do a right click, the right click is only gonna change the bottom left corner of the rectangle, like this. If I right click, so right click will only move the bottom left corner. If I want to change the rectangle, I have to use my right click. So right click will change the top right corner. Are you confused yet? It's confusing, but once you get used to it, it's easy. I don't know why they made it like this, but actually once you get used to it, it becomes quite easy. So right click will modify the top right corner. Left click will modify the position of the rectangle. Okay? Everything is a rectangle in Magic. Everything you do, you have to draw a rectangle. Alright. So, let's start. So like I said before, we already have a P substrate. I don't have to specify it. It's already there. You can imagine all this gray stuff is a P substrate. So what do I have to do? First, I have a P substrate, and then what do I need to do the PMOS? Yeah, I need the NWell. So let's do that first. I can't tell the size at first that I'm gonna need. So let's just make it this big, okay? In order to color it, that is to place the NWell, you have to find the NWell layer here. NWell. Okay, this is POL, this is NWell over here. And you middle click on it. Now most laptops don't have a middle click. I have a middle click on my laptop. Middle click is that middle button in the mouse. If you go to the Swamp Lab, the mice there have a middle click on them. So you middle click on the color here, on the layer, and it fills the rectangle with that layer. That's basically how you fill it. So you can see it's very unconventional working in Magic. There is another way to fill it without a middle click, but you're gonna have to use a command. Let me see if I remember that command. Oh, I just did something bad. Anyway, there's a command, but you have to actually write the layer and write. So this is much easier. Okay. So by the way, I wanted to show you some things here. When you start Magic, first make sure that that you're running the valid technology file, because sometimes there's an error and it loads a generic technology, not 90 nanometer. So in order to see that, you can look at lambda here. It says 0.09. Okay. So the next thing I'm gonna do is I'm gonna draw my diffusion layer. What kind of diffusion do I do in order to make a PMOS? Yes, N diffusion. No, actually, P diffusion. It's a PMOS. Diffusion is basically the drain and source. That's what it is. So the drain and source in a PMOS are P+, right? So P+ is P diffusion. So what I do is that I place the rectangle on the area I want to make the diffusion. And by the way, I'm making an inverter now. I haven't mentioned that. So I'm gonna make the width 8 lambdas, like that. And then I'm gonna middle click on P diffusion here, and it's gonna fill it. So now I have two layers on top of each other. Now I make a polysilicon. If I make a polysilicon like this, okay, if I make a polysilicon like this, don't mind these white dots for now, but what about this polysilicon? Is this what's my channel length here? So it's 360 nanometer. So this is wrong. What I need is 180 nanometer. So I press U to undo. That will undo. And then I do it like that. I place polysilicon. Now you can see here I have white dots. this means I have an error, a design rule error. If you look at this area over here, it says DRC equal 2. It means I have 2 design rule errors. I can correct them now, I mean, because I know them. But if I don't know what these errors are, I want to find out, I type DRC find, and when I do DRC find, it places the square on an error here, and it describes the error. So here it says poly overhang of transistors should not be less than 3. Okay, so what I do is that I have to fill this with polysilicon and this with polysilicon. Now, by the way, if you have something like this and then you do something like this, these become attached, become the same. They're not like separate, because they're the same layer and they're next to each other, so they become attached. And if I want to empty this area, I can fill it with nothing. The middle click fills the square, so if I middle click on nothing, it will fill it with nothing and delete everything that's inside. Okay, and the same can work if I middle click here, for instance. It's gonna fill this square with whatever I middle clicked on. So here it's gonna fill this with polysilicon, with P diffusion, and with NWell, all of this. But I don't want that, so I'm just gonna get rid of it. Let me make this symmetrical. Alright, so I have a channel now, and I have source and drain. Now, let me place my VDD. So VDD is always, first of all, let me place my contact, my body contact. So to place a body contact, what do I need on a PMOS? What kind of layer? We need N plus, right? So I search for N diffusion, which is here. Oh, I don't click it. Just that was an error. The minimum thickness, I think, is 3 for a contact. So I make the thickness, I make it 3 lambdas, and I middle click on N diffusion. Okay, now I have an error here. I know the error is that the extension beyond the diffusion should be at least 5, 6. I think it should be 6 lambdas, but okay, let's see what the error is. Yeah, so the NWell spacing should not be less than 6 lambdas. So let me add okay, I still have an error. That's strange. Okay. Okay, let's just hold on a second. Let me check something. Okay, so I made a mistake. You don't need to put N diffusion, because when you place this contact, it's called N substrate N contact. When you place this contact, it automatically places a diffusion under it. So you just need to place this contact. But this contact is too big. Like I said, it's more recommended that we do several smaller contacts. So just let me put my metal one, which is VDD, and then place. By the way, if I want to make my contact 3x3, my body contact, it's an error because the minimum size for the contact is 4x4. I can just do this.
How to know these design rules?
You can't know them. You memorize them as you work, because you have to correct yourself, and as you correct yourself, you start to memorize. So this is too close to the edge, and I have to move it. I can move it I can select it using S. If I put the mouse over it and I press S, it will select the contact. And then I can move it using the numbers 2486. 2486. This will move it up and down, or left and right, like this. Now I have these are very important to know, these shortcuts, and I have them on that PDF slide that I showed you yesterday. So I want to place a second one. By the way, if I select this contact like that using S, I can move it, I can copy it using C. So if I place my cursor over here and I press C, it will copy everything selected over here. This is how you can copy. So I just put it here and press C. Now these are too close to each other, so I have to copy it here, and then copy another one here. Okay, that's probably enough. Right? I think I can get rid of these. Yeah. I can minimize my layout like that. There only needs to be 3 lambdas after the contact. Okay. Now let me make my NMOS. Something wrong. So I middle click on polysilicon to extend it, and then I make my N diffusion. Now the minimum width we're gonna use in this course is 4 lambdas, like this. And you can see this is 8 lambda, so the width of the PMOS is double that of the NMOS. And now we're going to do the same thing. We're going to place the ground. I have an error here. I have to extend polysilicon. So the thickness of the ground connection should also be 4 lambdas. And then I place my contacts.
Should it be 3 times?
What's up? Oh, the PMOS? No, we do it just 2 times. Although the mobility is around 3 times the mobility of electrons, but 2 times will give us like enough performance balance that we need. So what kind of contact I have to place here? I have to place P substrate, P contact. And I have to place 3 of them. You should place as much as you can, as much as your area allows. Okay. So I connected the bodies of each transistor to ground and to VDD. Now I want to connect the source I need to connect the source to ground. Actually, I'm going to connect it from this side. And then I have to place an N diffusion contact. This is an ND, N diffusion contact. So I'm going to click here. So I connected now the drain to ground. By the way, I have to call this net ground, but I'm going to do that later. The same thing here. Metal 1, and then oh, sorry. By the way, if you press space by mistake, it takes you into another mode which have different behavior, so don't press space if you're in this window. If you do press it by mistake, press it 3 more times until you get back to this mode, crosshair mode. The other modes are actually very useful, but let's leave them to another session. So here I have to do P diffusion contact. Okay. Now let me connect my inputs. Okay, I made a mistake here. The source should be on this side because it makes the layout cleaner. So I'm just gonna select this, copy it here. Yes. What's that? P substrate is everywhere. It's you don't have to specify it. Right? Now what I did here is that if you put the rectangle like that and you press on Shift A, it selects everything under the rectangle. And then I copied it here. And then I come back here, I delete it, I fill it back with the layers that I need. Okay. Now this is the source of the PMOS, this is the source of the NMOS. These should be connected together, right? In an inverter. Alright, so let's do that. Let's copy this here. Copy this here. And connect them. Of course, if I place metal 1 like that, it will know that this contact reaches metal 1, this contact reaches metal 1, so these two are connected now. And I make way for the output to come to the edge like that. Now all that's left is the input, correct? So for the input, of course, one way is to just do this, be lazy and do this. And say this is my gate. You can connect your input here to the poly. Of course this would work, but it's a horrible design because all the inputs should be metal 1. This is the convention. And plus you don't want to make long connections in polysilicon because it slows down your circuit. So what I have to do is that I have to make a metal 1 here and then put a contact from metal 1 to poly. So let me do that. This is my metal 1. Let me place my poly here, and then this is called poly contact, and I have to use this one. Now I can move this to the, no I can't. See, this contact cannot be close to, okay, this is strange. Okay, anyways. So I just wanted to see what minimum distance I can have between my contact and the other metal. So you can see two metal connections cannot be close together more than 3 lambdas. So metal 1 cannot reach here. So I have the minimum distance for the contact is here. Okay. And this is a very, very important trick, but if you want to see which layer is connected to which, place your cursor over some area like that and press on S. Now S, the first time you press it, it will select the most obvious rectangle under it. If you press it a second time, it will go through all the connections, through all the contacts. So here it went through the contact and it selected my other connection, which is a polysilicon. So now I know my metal here is successfully connected to the polysilicon. The same thing can be done here. So if I press it once, it will select this rectangle. If I press it a second time, it will go here. And the third time, it will go here. Okay? And then I can press comma just to remove all my selection. Right. Now, it's always nice to have some symmetry in your circuit, so let's just make them on the same level. And by the way, I can probably make this more compact, reduce the area. For instance, here I can select this and I can move it up. Oh, this is too much. Oops. I can move it up like that. And I can probably move this down. Shift A will select everything under the rectangle. A will select there's a difference between A and Shift A, but it's in the manual. I can't remember it. Shift A will select something other than A. I can't remember really, but I just use Shift A and I bring it down. Okay. Now this is a pretty small height. I can even take this up like this. Oops. Oh, you don't need to do Shift A will only add to the previous selection. A alone will select what's under the rectangle. Okay, so I can move this up like this, and then I can probably move this up. You get the point. I can make it very compact, but this is not gonna matter because, like I said before, all the gates should have the same height, and my XOR gate will be much bigger than this and will have a higher height. So in the end, I have to change the height of my inverter to extend it to that it will be equal to the other gates. But just to prove a point, I just did that.
So you have to make it at the end, and do it at the end of our design, then compact everything.
Yeah, you can do that too. It's probably better to start with the XOR gate and then do the other gates. Now there are other cells, like a multiplexer for instance, or a flip-flop. They are much bigger than regular cells, and they take 2 times the height. If it's 2 times the height, then they can align with other gates. If you place 2 other gates on top of each other, they would align. But you don't have to worry about that now. I have one final step left to do. Can anyone say? What's that?
Whether it is working, inverter is working.
Before that, remember, yes, I have to name my nets. To name your net, you for VDD and ground, you take your rectangle and then you left click it on the bottom left corner so that the rectangle is actually a point, and then you place the point on the net you want to label. Then you go to the command line and you say label VDD, and for VDD and ground, because they are global nets, we place an exclamation point, so it places the VDD label here. Okay, so all of this is VDD now. Sorry, this is VDD, and I do the same with ground. Label GND. So GND is ground. Now inputs and outputs, they also have to be labeled. My input, for inputs and outputs, I prefer to have terminal and not just labels. For terminal, I make my rectangle a line. Make it a line and I put it over here. And I say label, say in. And I come here and say label out. Okay. And this is it. You should always look here to see that you don't have any design rule errors. Alright. Okay. Now I need to test this, right? But how do I test this? The way to test it is, of course, using HSpice. But HSpice only takes netlists, it doesn't take layouts. So there's an additional step to convert my layout into a netlist. And Magic can do that for me using two commands. The first command is called extract. It's more recommended to do extract all so that it goes through all the levels if you have multiple abstraction levels of cells. So when I do extract, it makes it netlist, but in a format that's not useful for me, in a format that's compatible only with Magic, which is in a file called, by the way, oh, I forgot a very essential step, which is to save my circuit. So to save it, I just do the command write. Is it write or save? Okay, it's write cell, no write all. Hold on a second. Let me try write my inverter. Oh, it's save. Okay, so I saved it as my inverter. Okay. You can also save from here if you've already saved it. I think do file, save, sit. Okay. So you should always save. By the way, Magic is a little bit, I mean, the whole Unix environment over here is unstable. Your account may become full because of your quota, and if it becomes full, Magic starts to behave strangely, and it would crash, and all your work would be gone. So I very heavily recommend saving a lot and backing up your file. Like every once in a while, if you're working on your project, back it up, put it on a flash drive or something, because this is not a very trustworthy software, and you don't want to start over from scratch. So I do extract all, and it generates my inverter.ext, but I want a SPICE compatible netlist. So I use another command to convert this netlist to SPICE, which is ext to SPICE, and I write my inverter. Okay. Now I'm gonna exit Magic. Use quit. You can also use exit, but quit is more recommended because it doesn't generate it cleans up your mess when you do quit. If you do exit, sometimes it doesn't clean. Now let me check my inverter.spice, which was generated. So Magic first puts the option scale is 0.09 micro. If it does this scale, then you can see that the length of when I have M, a line that starts with M, that is what? It's a MOSFET, right? It's a MOSFET. So MOSFET, drain, gate, source, and body. So it's all correct. The PMOS is correct, connected correctly. It's a PFET, PMOS. W is 8. 8 times the scale, which is 8 lambdas, so it's correct. This is correct. Now, AD is area of diffusion, and then perimeter of diffusion, then other things you don't care about. This is the NMOS. It's also connected correctly. I'm not sure why this ground is capital. That is strange. Any case. Okay. Now, if you remember from your homework, I'm gonna need a model file because transistors are kind of complicated and they need model files. So I need to get my model file in order to simulate that. Now, I don't remember where I have my model file, so let me just find it. Oh, there it is. Okay. So I got my model file. Now let me create a new text file to simulate my circuit. my inf test.sp. First line is always wasted, so let me just write sim file. And now I have to include tsmc18.sp, and I have to include my netlist that I just generated from Magic, okay? Which is my inverter.spice. And now I write my simulation code. Let me place a voltage source on in. Well, first of all, I need to connect VDD and ground to power sources, right? So I need a voltage source V1 from VDD to ground, and we use 1.8 volt in 18 in this technology. Okay, so I connected VDD and ground. I put a voltage source between VDD and ground of 1.8 volt. V2 is gonna be a pulse, and it's between in and ground. It's gonna be a pulse of between, say, 1 and 1.8, 0, and 0. Let's use 50p for rise time, 50p for fall time. And then for the pulse width, let's use 1 nanosecond, 2 nanoseconds for the period. I'm not sure if these parameters are in the right place, but I can correct that later. And then dot option post. I don't need more options. Actually, probe would be useful if I have a large circuit. And I make a transient analysis with a step size of, say, 10 pico, and it stops at 2 nanoseconds. And then I probe V in and V out, and that's it. End dot end. Okay. So let me run this file, my test. I'm sure I have some errors there. Let's just check. Yeah, I do have some errors. Oh, it's a typo. Yes. Okay. Now let's do C-scope. And you can load plot files from the command line like this. My inf test.tr0. This is in and this is out, which is what an inverter is supposed to do, right? Invert my input. So if I wanted to see how fast my inverter is, although this is not a fair test because the inverter is not driving anything, but let me make it faster. Let me make the period 0.4. Do it again. So you can see my inverter is a little bit slow. My output doesn't rise immediately. It rises like that. And it's not even driving anything. Now if my inverter was driving another gate, this here, where you see the cursor is, would rise like this. If it was driving 10 gates, if I was driving 10 gates from the single inverter, it would rise even slower, like this. And this is very very interesting to see, like, because you have to modify the width so that it's faster. You can have a faster circuit. Okay. So are you convinced that the inverter works correctly? Okay. One last thing I want to show you before we go. If I wanted to open my inverter again, I can do mag -9 my inverter.mag, and it will open it up. If I wanted to open it up from inside Magic, I can say load my inverter, and if I press tab, it will complete it. Inverter. Now if I want to start another circuit, I can say load other layout, and it would start another layout.mag. Oops. Okay. And then always remember to enable the grid using G. If I wanted to get my inverter and use it here, this is very important. I do get cell, okay, my inverter, and bring the inverter like this. And I can do whatever I want with this. I can copy it again. And it will give each one a different name, an instance name. If I go into my inverter cell and modify the layout, it will modify each of these three, because these are only references. They're not separate copies. Okay? If I wanted to see what's inside, I have to select everything and do X. X will expand. X is for expand. If I want to hide it again, I just do Shift X. I prefer to hide it because there's no meaning in keeping it like that. Now you might want to change your inverter like this from here. You can't. This is not editable. If you want to change it, you have to go to the inverter cell. You can't see, if I wanted to delete this like this, I can't. I have to delete the whole cell if I want. Okay? Any questions? Okay, so I guess you're ready for the second homework for Magic. Don't worry, it'll just be what's that? Well, you know, for your projects, when you do your project, you have to have you should already have done your basic gates, because your project will be just placing those gates and connecting them. So your first homework will be to make those gates and simulate them, and then these gates you'll use them in your project. I mean, you're gonna have to make these gates anyway. So this homework is just it's just practice. It's just one step of your project, really. And don't worry, you'll have enough time to do it. Like 2 weeks or more. Okay. And I'll also post this video on YouTube.